All right, going through these. Um, so looking at these reactions. So the first one says how many moles of iron 2 dichromate are needed to react with 3.44 moles of oxygen. So the first thing you need to be able to do is figure out which formula represents iron 2 dichromate and which formula represents oxygen, which should be kind of easy, but some people are still caught up on that. All right. So looking at this, what are we starting with? What's our given? 3.44 moles of oxygen. All right. So that's where we're starting. Iron dichromate. So this is our oxygen. Iron dichromate is that. All right. So we need to go from moles to moles. So I set that up. I'm going to start off with my 3.44 moles of O2. And then there's 4 moles of iron dichromate for every 1 mole of oxygen. And then what we would need to do is solve. So how many sig figs should my answer have?
1.
You should know by now.
It's 3.
All right. Looking at the second one. Now, I just used whole numbers on my molar mass for this one for convenience for myself. You should always be going to 2 decimal places on it. So your answer may be slightly different than mine, but it should be close enough. All right. So for the next one, it says how many moles of oxygen must be burned from 22.55 grams of potassium dichromate. So this time we're starting in grams and we're going to moles. On the test, the units will not be underlined and bolded like that. I'm just trying to help you start seeing where to look. Should get a very small number. What should our answer be? How many sig figs should it be? It should be 4 sig figs. All right. 0.01453 is your answer. So you should have it in 4 sig figs. That is your molar mass. I just didn't do it to 2 decimal places like I normally do. All right. Now, so you need to make sure that you have your POGL and your little spider diagram that I gave out on Monday. If you didn't get one, they're up front. You need to grab one. All right, so we're going back through and answering the ones that I assigned for homework on Monday. All right. And you should have a packet for the POGL too. All right. Do you have this? You were here on Monday, weren't you?
Yeah.
This is what we're looking for, is that packet. That was what we did our notes in. All right. So again, I assigned problems number 7, number 16, number 17, and number 25. So going through on this one, we had methane, which is CH4, reacts with sulfur, which is S8, to produce carbon disulfide and hydrogen sulfide. And then I asked you to do parts A, B, and C on this. So going through there, when we write the chemical formula, it should have been 2 moles of CH4 plus 1 mole of S8 reacts to form 2 moles of CS2 and 4 moles of H2S. Part B asks us to calculate the moles of carbon disulfide that's produced when 1.50 moles of sulfur are used. So I start off by writing my given. I have 1.50 moles of S8. And then I'm going to, in this one, I'm going from mole of A to mole of B. So when you did this calculation, I'm going to put 1 mole of S8 on the bottom. I'm going to put 2 moles of CS2 on the top because that's my coefficients. Sorry, 1 and 2. So 1.5 times 2 into 3 sig figs is 3.00 CS2. All right. Now, part C didn't actually give you a given, but what I want to show you is we can start off.
Excuse me, Mr. Martin?
Yes.
Okay, I need 2 students to the front office, okay? So
Nope.
it's Michael Reed and Edie Napolitano.
Okay.
Thank you.
What'd you guys do?
We pulled the flower.
All right. So going through this one, it didn't matter. It didn't matter if you started with your original given or if you started with your answer from your original problem. You're going to come up the same thing. So if I start with 1.5 moles of S8 and I establish my mole ratio that I have 4 H2S to 1 mole of S8, I get 6 moles. If I started using this one where I had 3 moles of carbon disulfide, I see that I have a ratio of 4 to 2, and guess what? The answer is 6 moles. That's why we have to use mole-to-mole relationships, because if we have a balanced chemical equation, doesn't matter where our starting point is we can always get to the same answer. All right. So remember that Model 1 was a representation of a mole to mole. So we're going from mole A to mole B. So if we're looking at it in terms of our spider diagram, so we're hanging out on this one. We were hanging out right in this little section right there, just using the mole ratio, just using that conversion factor. All right. Moving forward. Questions 16 and 17. All right. For question 16, it gave you the chemical equation that was already balanced. So we had 4 moles of phosphorus plus 5 moles of oxygen reacts to form 2 moles of P2O5. It asks us to solve for the molar mass of P2O5. That should be 141.94, I believe. Pretty sure that was what I got earlier. Yeah, 141.94. All right. So when we did this one, it says how many grams of P2O5 are formed when we have 3.4 moles of O2. So in this relationship, I'm starting off with moles of O2. I need to get from moles of O2 to P2O5, and I can only go from moles to moles. All right. So I'm going from moles to moles, and then I can go to mass, P2O5. All right. So when we set this up, I'm starting off with my given. How do I get from mole of O2 to mole of P2O5? What process am I using? Mole ratio, thank you. So I'm getting rid of mole of O2, and I'm trying to get to mole of P2O5. And so I'm going to look at my balanced reaction. I have 5 moles of O2 for every 2 moles of P2O5. So that got rid of my oxygen. Now, how do I get from moles of P2O5? I need to use the molar mass. So I'm going to use the molar mass of P2O5. I'm trying to get to grams. Remember that molar mass is always relating to 1 mole of the substance. So, going back through it, if I'm starting off in moles of oxygen, I have a molar relationship of oxygen to P2O5 that is 5 to 2. So 5 moles of oxygen for every 2 moles of P2O5 produced. My molar mass of P2O5 for 1 mole is 141.94 grams. So now we go ahead and solve it. Our answer should be in 2 sig figs. What do we come up with? Seen a lot about priorities. What should my answer be? 190. My given's only 2 sig figs. My answer can only be 2 sig figs. I got 193 in the calculator. I have to maintain the value. Yes? Not 19 times 10 to the 1. Because that's not correct format for scientific notation. 1.9 times 10 to the 2.
Oh, yeah, you're right.
All right, looking at the next one. So we had acetylene gas and calcium hydroxide are produced by adding water to calcium carbide. So my chemical reaction should look like this. takes 2 moles of water for every 1 mole of calcium carbide. That forms acetylene, C2H2, and calcium hydroxide. So it says, what is the molar mass of acetylene? So I have 2 carbons, and that should be 12.01 here. I don't know why it didn't update. All right, 2 times 12.01 gives me 24.02. And then 2 hydrogens, 2 times 1.01 gives me 2.02. So my molar mass is 26.04. All right, now, so this one says how many grams of acetylene are produced by adding 3 moles of CaC2, and then show your math below. All right, so starting off with the 3 moles, notice that in the balanced equation that calcium carbide and acetylene are a 1-to-1 ratio. So mathematically, that doesn't change anything. So all we're really doing is multiplying the 3 moles times the 26.04. I can only have my answer in 1 sig fig. I believe the calculated answer is something like 78, but I have to round it to 1 sig fig, so 80 grams. Yes.
How do you know when to put like a number in the denominator and when not? Because the last time I put 5 in the denominator, just use 3.
Mole ratio always comes from the coefficients. I would recommend that you watch the video that I recorded Monday. All right, so looking at the bottom one, it said how many grams of CaC2 are needed to react completely with 490.0 moles of H2O. So in this case, we started off with mole of H2O. We have to get rid of mole of H2O. So I have 2 moles of H2O for every 1 mole of CaC2. Molar mass of CaC2 is 64.09. When we do that calculation, you get something like 15,704, something like that. Putting it into 4 sig figs is 1.570 times 10 to the 4th. Which another, if we were entering this in as a answer on the test, I probably would have did 1.570 E4 like that. That means the same thing. All right. Last one. Last one based off of what we were doing. Sorry, I was looking at something. All right, so going through here again, I'll actually update this to what it should have been, 47.87. So that should be 47.87. This is 32.00. So 9.87. So that would have been 9.87. 9.87. And so going through here, if we started off with 1.25 grams of titanium oxide, we have to get to moles of titanium oxide first. So this one is going from mass to mole to mole. So 1.25 divided by 79.87, and then times 2, we get 0.313, maintaining 3 sig figs. For part D, we started off with 1.25 grams of titanium oxide again. So divide that by 79.87. And then it's a 1-to-1 ratio. So on this one, the only change, 0.157. I'm going to tell you on the test, either one of those answers would have been acceptable, but the preferred answer is 0.0157. Because Southeastern wants us to go to 2 decimal places on molar mass always. So that's going to make the difference in our calculation. All right. So in this one, so at this point, and I'm going to do this right here, we've had 3 models. We had model 1, which was going from mole A to mole B. So mole of one substance to mole of another. We used mole ratio to get there. Model 2 was mole of A to mole of B to mass of B. So we went from mole of one substance to mole of another substance to mass of a substance. Model 3, at this point, we did mass of A to mole of A to mole of B. So if you had to guess before looking at model 4, or actually it's model 3 in your packet, but before looking at the next model, what do you think we're going to do for our next step? It's going to be mass of A to mole of A to mole of B to mass of A. Mass of B. All right. So go ahead in your packet, change this to model 4 because I'm going to refer to it as 4. They didn't number the second part, the model before that. All right. So we have the same equation that we've had in every model. Nitrogen gas plus 3 moles of hydrogen gas reacts to form 2 moles of ammonia. All right. And it gives us the question or prompt that says how many grams of H2 gas are needed to produce 34.8 grams of ammonia. All right. So in model 4, I am given a mass. All right, so in this case, I'm given 34.8 grams of NH3. I need to get to mole of A. So I need to use my molar mass. So 1 mole of NH3 is a certain amount of grams of NH3. Specifically, it's like 17.02. No, 17.04. Sorry. But in my calculation, I'm just going to use the 17 for ease of use today. All right. Now, and then, so we're in math. We went from mass of A to mole of A. We need to get to mole of B. Our B in this case is whatever our unknown is, which is H2. So I'm going to moles of H2 from mole of NH3. So where do I find the numeric relationship of H2 to NH3? Coefficients. So I have a 3 and a 2. And then lastly, all right, so that's kind of our basic steps of what we did. All right, so the last step is I'm trying to get from mole of B to mass of B. The thing that I want you to understand, every one of these calculations, every step that we've done here is something that we did in chapter 6. In chapter 6, we were just doing it within one formula. The only thing new that we added is to be able to go from one formula to another formula. And that's through that mole ratio. All right. So going through these questions real quick. What's the given in this example? And I'm going to ask you to be specific. 34.8 what? Grams of NH3. The reason why I'm asking you to be specific is they haven't asked it in this whole packet, but what's our unknown in this? What are we looking for? So I want to know how many grams of hydrogen. So I have to be able to figure out the pathway to get there. All right. So if I relate this back to my little spider diagram, on this one, the pathway that I'm taking is there, right? I'm going from mass to mass based on your little spider diagram. So the 3 steps to solving this one is I need to, first step is to convert from mass of A to mole of A. So that's step 1. Step 2 is mole of A to mole of B. And then step 3 is mole of B to mass of B. All right, the way that I get there, 1 mole over the molar mass over here is going to be mole B over mole A. And then here, it's molar mass over mole. All right. So now, when any type of stoichiometry problem, what unit do we need to get to first? What's the first unit we always have to be in? We must be in moles first. And the reason why is because moles is the only thing that translates within a balanced equation. So when we balance the equation, we are balancing it based off of moles. I can't relate mass directly to mass. I can't relate volume directly to volume in this case when I'm looking at a balanced equation, but I can relate mole to mole. All right. So now, number 30, it says, where does the 3 over 2 come from in this one? It's the mole ratio from the balanced coefficients. All right. So the 3 moles of H2 to 2 moles of NH3 is the mole ratio of the balanced coefficients. All right, moving on. All right, a couple of more things and then we'll actually solve it. All right, so explaining some other parts of this real quick. So looking at number 31 with the same model. So where does the 2.0 grams of hydrogen to 1 mole of hydrogen, what is that? That is the molar mass of hydrogen. Now, if you were doing this on your own, I would recommend that you look at it as 2 decimal places in your molar mass. So 2 times 1.01 would be 2.02 grams per mole, instead of saying 2.0 like they did in the text. All right. Number 32, where it's 1 mole of NH3 to 17 grams of NH3. What is that? That is molar mass of ammonia. And again, so I would look at this more. We have 1 nitrogen, 3 hydrogens, if you were doing this on the test or an active, you would probably want to use the 17.04 grams per mole. Now, for 33, again, I just want us to verify that you can enter it in the calculator and get the expected answer. The expected answer is 6.14 grams. So if I'm entering this in the calculator, I'd start with my 38.4. I'll multiply my first fraction, which is 1 over 17, times my second fraction, which is the mole ratio, which is 3 over 2, times my third fraction, which is 2.0 over 1. And you should come up with 6.14 if you did that correctly. All right, questions on that? So let's look at this in use and in context. All right, so question number 34. I want you to take a minute and I want you to do parts A, B, and C on your own. I'm going to set a timer for a few minutes and then we'll go forward. All right. So going through this, molar mass of P2O5, you should have gotten 141.94. Molar mass of oxygen, you should have gotten 32.00. All right. So looking at the prompt, it says how many grams of P2O5 are formed from 3.4 grams of O2. So I'm starting with grams of oxygen. The first step is to get to moles of oxygen. After that, I can go from moles of oxygen to moles of P2O5. And then from there, I can go from moles of P2O5 to mass of P2O5. So starting off, my given is 3.4 grams. What's this first fraction going to look like? All right. What's this fraction going to look like, my mole ratio? 2/5. And then what is this fraction going to look like? All right. So when we solve that, my answer should be in 2 sig figs. So what do we come up with? 6.0. Two moles of P2O5 for every 5 moles of O2. It can be any two things. It can be any. So with stoichiometry, I can compare any two things in there. I could have compared phosphorus to that, but we didn't have a given for phosphorus. So I can compare any two things within the balanced equation. Since we've balanced it, I can compare one thing to anything else. It can be two reactants, it can be two products, it could be one product, one reactant. It can be one reactant, one product. Be reactant to reactant, product to product. All right, that's why we have to get to moles, because that's what that allows us to do. All right, number 35 is going to be, that's the one I'm going to start with tomorrow. So do this one at home. Don't try to do it right now because we're going to move on to the next model. All right, so the next model is really and truthfully looking at, if we look back at our spider diagram. So I have mass, volume, particle, mole, mass, volume, particle. All right. So what I want us to start recognizing in this one, I'm going to talk about what this model is, taught in just a minute. But if you want to call this one Model 5, you can. Model 5 is really looking at how we can take pieces, parts, and build any equation from this. So what I want us to understand is, so far we have done mass to mole, we have done mole to mole, we have done mass to mole, we've done mass, we've done mole to mass, and then we've done mass to mole to mass. So we can start at any one of these parts, and we can end up at any one of these parts depending on our conversion factors that we use. This conversion factor is always going to be the moles of the new substance over the moles of the original. That's your mole ratio. So this is the A side, that's the B side. All right, so now let's look at our model and let's look at what it says. So model gives us the same chemical reaction that we've seen multiple times in this POGO. Nitrogen gas plus hydrogen gas forming ammonia gas. All right. The question this time says, how many liters of nitrogen gas are needed to produce 38.2 grams of NH3? So if we look at this one, I'm starting in a mass. I'm going to mole. I'm going to mole. And this time I'm going to volume. So if I'm looking at my reaction, I'm starting here. I have to travel through here, then to here, and I'm going to end up there. So on Monday, I gave us a relationship. What relationship did I say that 1 mole of a gas equals to in liters? 22.4. So this only works for gases. If it's a solid or liquid, we have to use density. And so we would have, so there's technically another circle here, volume of a solid or liquid, that we would have to travel through density here. So if you're dealing with a solid or liquid, we have to go from volume to mass first, and then we can go to moles. But if we're dealing with a gas, we can go directly to mole, directly from mole to volume. All right. So we have this established relationship. This is called the molar volume constant. that we're going to use. So let's kind of look at this one. It says, what is the given? So what is the given in this example equation? So we're starting off with 38.2 grams of ammonia. My unknown this time is liters of nitrogen gas. All right, so that's what we're trying to get to. So looking at the problem that they set up for us, where does this 22.4 liters of nitrogen gas to 1 mole of nitrogen gas come from? It's our molar volume. It's our molar volume constant. Where does the 1 mole of N2 to 2 moles of NH3 come from? That's the mole ratio. Remember, that comes from the coefficients in the balanced equations. All right, and where does the 1 mole of NH3 to 17 grams of NH3 come from? That's the molar mass. Molar mass of ammonia. All right. Let me check something real quick because I don't think I added the slide I need. All right. So it didn't ask us to do this in the POGL, but just like before, I want to verify that we come up with the right answer. All right. So, and actually this one is not going to come up with the answer they put. They actually have the wrong answer in the packet. So we're starting with 38.2. I need, and then I have 1 over 17. And then I have 1 over 2. And I have 22.4 over 1. When we do this calculation, what should our answer be? Say it again. 25.2. So I think they were. I think they went back to grams of nitrogen instead of volume. All right. So when we're looking at this, when we're kind of going through this, they're not always going to be nice and give us formats that we've seen. Sometimes you have to build the format yourself, and that's what I want to make sure that you recognize. So let's go ahead. Let's look at example 41 together, and then we'll kind of wrap it up. It says, given the following equation, how many liters of H2 gas are produced from 3.5 grams of HCl? So I'm starting with 3.5 grams of HCl. I want to know how many liters of H2 gas. So hydrogen is a gas. Can I use the molar volume constant? Yes, it's a gas. All right. So I'm starting off with grams of HCl. What's the first step that I need to get to? I need to get to moles of HCl. From there, what can I do? I can get to moles of H2, and then from there I can get to liters of H2. All right. So if I'm starting off with 3.5 grams of HCl, how do I get to moles of HCl? All right, so for every 1 mole of HCl, I have, so chlorine is 35.45 grams per mole, and hydrogen is 1.01 grams per mole, so that is 36.46 grams per 1 mole. All right, now I need to get rid of moles of HCl. I need to get to moles of H2. So looking at my balanced equation, I have 2 moles of H2 for every 1 mole of H2 for every 2 moles of HCl. And then lastly, I'm going to use my molar volume constant for every 1 mole of H2. I have 22.4 liters of H2. How many liters of H2? All right. So when we do this, we have to maintain 2 sig figs. I get 1.1. Because I get 1.07, that rounds to 1.1. All right. So now, at this point, you should be able to go from kind of any one substance, one type of thing to another, but what you have to understand is the relationships. So looking at question 43, if I wanted to convert between atoms, formula units, molecules, and moles, what whenever we say atoms, formula units, or molecules, what are we talking about there? Particles. All right, so if I wanted to go from particles to mole, how would I get there? Avogadro's number. So if I have my particles on the bottom, if I'm going from particles to moles, I'm going to put Avogadro's number on the bottom, right? It's 1 mole. What if I was going from mole to particles? Bless you. How does that change? Avogadro's number's on the top. Notice on your spidergram, on the B side, you're always multiplying by the conversion factor on top over 1 mole. On the A side, it's always dividing by the conversion factor. All right. So how do I set it up to get from mass to mole? So 1 mole over molar mass in grams, right? How do I get from mole to mass? All right. Number 45 is probably the most important question on the whole packet, because this is kind of the sum of everything in there. What is the only conversion factor that can be used to convert between 2 different substances? So mole to mole. We can only go We can only use that balanced equation when we're in terms of moles. So I can go from mole A to mole B. The mole ratio is always mole B over mole A. Our original substance are given to our unknown. All right, there's no two steps with that. We're not ever going to do it the other way. All right. What conversion factor is used to convert between moles and volume? So if I'm going from mole, well, actually, let me do it the right way. Let me do it from A side to B side. All right, if I'm starting with volume of a gas going to mole, how do I set that up? So if I'm starting in volume, I'm going to divide by 22.4. If I'm starting in moles, it's 22.4 over 1. All right, questions on that? All right, so let me find this. Along with the other problem that I assigned in your POGL, these two problems also I want you to do, and this is where we're going to start tomorrow. Yes, if you're going to see her. All right.
Personality-wise, I think our personalities are different.
Make sure that's only 2. Yeah. All right. Can one of y'all do me a favor? Go knock on Coach D's door and ask him to check his printer and see if I have more copies on his printer. Go ahead, Devin. He's across the hall.